Hey guys, welcome back to my channel. So today we're gonna discuss the second video for our MCAT physics fluid series. So in our second video, we're gonna discuss hydrostatic. So hydrostatics is the study of the systems involving fluids that are not in motion, right? So if you haven't watched the first video where I talked about the basics of fluids, please do so. Okay, now let's jump right into hydrostatics. So a really quick recap from the last video. Hydrostatic pressure is some sort of a gauge pressure that doesn't take the atmosphere pressure into account, right? If you want to take both the atmosphere pressure and the gauge pressure into account, then that will be the absolute pressure, right? But just the gauge pressure as hydrostatic pressure is some sort of pressure experienced by an object that is submerged in some sort of liquid, right? And then the pressure the object experiences from that liquid above the object, surrounds the object, right? Okay, and then to quantify the hydrostatic pressure, capital letter P equals the density of the liquid. The liquid can be water or blood or some liquid mercury, right? So the density of any liquid times the gravitational acceleration times the depth of the submersion, okay? And then that will give you a value in unit of Pascal, okay? All right, so now let's talk about buoyancy. So buoyancy is actually quite intuitive, as in our daily life, we see things being able to float on liquids, right? So intuitively speaking, if an object has a lower density compared to the liquid, it will float. If an object has a higher density compared to the liquid, it would sink, right? Okay, but now let's use some MCAT languages in terms of specific gravity. Let's talk about when does an object has a buoyancy, okay? So let's use water as our base liquid. So when an object has a specific gravity that is less than 1, if you recall from the last video, that means it's less dense than water, right? Then it will be partially submerged in water. So now the question is, since I said partially submerged, you might want to ask, then how much exactly does it submerge, right? So to quantify that, actually the percentage of submersion is actually equals to the specific gravity times 100. Okay, what do I mean? To give a couple examples, if an object has a specific gravity of 0.2, right, then 20% of this object will be submerged in water in this case, okay? Or if another object has a specific gravity of 0.98, which is higher than 0.2, right? But still less than 1, okay? Then 98% of this object will be submerged in water, right? So to show it on the graph, and then I have two objects. So the first object has 20% of its volume submerged in the water, right? Whereas the other object really have the vast majority of its volume, 98% of its volume submerged in the water, okay? All right, and then whenever you throw an object in liquid, that will cause some displacement of the water, meaning the water level, the surface level would rise up, right? So actually, like how much does the throwing, let's say this ball into the water, cause the water to rise up, depend on how much this part is submerged in water. Let's say 20% of the ball's volume is submerged in water, then the same amount of volume of water is actually got displaced, okay? All right. So now let's talk about the object has a specific gravity that's equal or larger than 1, okay? So in this case, 100% of its volume will be submerged in water, right? It will be sunk to bottom, and 100% of its volume will contribute to the displacement of the water, meaning the volume of the displaced water in this case will equal to the whole volume of this ball, okay? All right, so now let's talk about the force, okay? So all these three balls, they're experiencing two different forces, right? So very obviously, the downward force each ball is experiencing is the gravity force, aka the weight of the balls, right? Due to the mass of the earth and also the mass of the ball, right? That gives the gravity force. But there's also some different direction force called a buoyant force. That is lifting up, kind of pulling up the ball, right? So that it kind of floats, right? So it's really whether a ball sinks or floats is really a competition between the buoyant force versus the weight, right? So if a ball sinks in this case, then obviously the gravity force in this case will be larger than a buoyant force, right? And then when a ball is rising upward, that means the buoyant force is larger than the weight, right? But what about when the buoyant force is equal to the gravity force, or aka the weight? Would it float or sink? It would actually float, okay? So it will float like that. 50% of the ball out of the surface and 50% submerging water, okay? All right, but this is a float status, okay? All right, and then to quantify the value of buoyant force, a guy named Archimedes figured out the equation for calculating the buoyant force is actually mg, okay? And then this m is the mass of the displaced water, okay? And then when we talk in our first video, when we discussed density, we say density is basically mass over volume, right? So that gives me mass equals to density times volume. So here the buoyant force can also be expressed density of any liquid, in our case water, times the volume that the water has been displaced, which is also the volume, how much of the ball that submerges in water, right? Times 10, which is the gravitational acceleration. Okay, so that's what Archimedes figured out, how we quantify the buoyant force. Okay, and then for the case of fully submersion, my density of the liquid times V times G. Here, this V is just 100% the object's volume, right? Okay, so this V and this V, they're not describing the volume of the object. They're the volume of the displaced water. But here, because this displaced water's volume equals to the volume of the ball. So that's why this V is the 100% the object's volume, okay? Okay. Whereas here, this V, how much the water got displaced, how much volume does the water get displaced, you can just, it's just the same amount as how much volume of the ball is submerged in water, okay? I hope that makes sense. So really quickly, I want to show you a very MCAT style problem regarding this, okay? So it says that, so I have an object, okay? So I know three values about this object. First, the object's specific gravity is 2, okay? And then it also tells me the object has a volume of 1 meter cubed, okay? And then it also tells me the object weighs 2,000 kilogram, okay? Oh, pretty heavy, okay? So it asking me like what is the buoyant force when this object is interacting with water, okay? So first, from the specific gravity, I know that the object is fully submerged in water, right? And then I also know that the density of the water is 1,000 kilogram per meter cubed, and then times the volume of the water that's displaced, which equals to the volume of this whole ball, because this whole ball is just wholly submerged, right? So it's 1 meter cubed. Okay, times a G, which is just 10, right? So that will give me 10,000 Newton, right? 10,000 Newton. Okay, so I didn't even use the mass of the ball, 2000, right? So this is very MCAT like. So it will throw you the information that you might not need for solving the question, okay? All right, so that's all about buoyancy and Archimedes' law. So now let's move on to Pascal's law, okay? So what does Pascal's law say? So Pascal's law basically was just saying that, okay, a change of pressure made at any location within an enclosed fluid system will be transmitted equally to all points throughout the liquid, okay? So as fancy as it sounds like, basically it's just saying, okay, this enclosed fluid system, here. Every single point of this system, we have a constant pressure. That's what this is eventually talking about, right? So let's say this point is a point 1, okay? And then this point is a point B, okay, point 2, okay? So they have the same amount of pressure, so which P1 equals P2, right? Okay, according to Pascal's law, okay? And then also according to the definition of a pressure is just a force per area, right? So P1 will be F1 over A1, right? And then A1 is just basically this cross-section area, right? Okay, and then let's say the P2 is just F2 divided by A2, right? And then what is A2? A2 is the larger cross-section, larger area here, right? On the car side. Okay, let's actually use different, very different color to kind of differentiate it. Okay, all right, perfect. Since P1 equals P2 according to Pascal's law, so F1 over A1 would equal to F2 over A2, right? And as you can see that A1 is obviously smaller than A2, right? So that would make F1 has to be smaller than F2 so that a P1 can equal to P2, right? So this is basically the application of Pascal's law using this hydraulic system, okay? So we can control the area, right? We can control the area. And then so that our input force is here, input force at point 1 is way smaller than the output force at point 2, right? So basically we're using this hydraulic lift that takes advantage the Pascal law to have some mechanical advantage. And remember when we talk about work and energy, we said mechanical advantage is to leverage a physical setup to be able to perform the same amount of work with less input force, right? Here, F1 is the input force. It is smaller than F2, which is the output force, right? Without this hydraulic mechanical advantage setup, the output force will be equal to the input force. Then the output force will be the weight of this heavy car, F equals mg, right? The mass of the car times 10. So that's what we have to exert without this hydraulic lift setup. But now with the control of the area, A1 smaller than A2, we can have a smaller input force, which is F1. Okay, I hope that makes sense. Okay, and then another thing worth noting is that we know the work performed on both sides is the same, right? So W1 equals W2, because that's a definition of a mechanical advantage, right? To leverage a physical setup to be able to perform the same amount of work with less input force. So if W1 equals W2, then F1 times D1 has to equal F2 times D2, right? And then we know that F1 is substantially smaller than F2, then D1 must be larger than D2, right? Which means this force travels, if I have some apparatus here, then I press the button. The input force go this way, go this way, go this way, go this way, this way, right? All the way that it'll lift up the heavy car, right? So this is the trend of this force, this input force, right? Okay, it would eventually lift up the car. But how many distance does the F1 travel here? The D1 that goes down, that goes down, D1, is very, very much larger than the distance that D2 travels, the car travels up, right? Okay, so you want to know that when you see this hydraulic system, you want to realize the heavier side, the side where we have a larger surface area always moves over a smaller distance, okay? All right. So now let's talk about surface tension, okay? So surface tension, what causes surface tension, okay? I guess to ask this question, let's ask another question. Like, how does a molecule, how does a liquid hold together, right? So let's say we have a lot of water molecule, okay? So a lot of water molecules get together. They have to have some sort of intermolecular force, right? Between the water molecules so that the whole thing make up a whole liquid, right? All right. So the intermolecular force experiencing, let's say we have a lot of H2O here. And then the intermolecular force in the case of water is a hydrogen bond, right? But we can also have London force or some hydrophilic interaction like a disulfide bond, right? They can all link the different molecules together, aka intermolecular force, right? Whereas the covalent bond, that's not a intermolecular force, that's intramolecular force. That's the bond between this one molecule, right? That is my covalent bond. So the intermolecular force that hold a molecule together are usually hydrogen bond, London force, or any sort of hydrophilic interactions. Okay, so let's look at the water molecules. Okay, so the water molecules. Let's see, for example, this guy. So this guy is really satisfied because it's like experiencing the same amount of intermolecular force from all directions, right? It has a really balanced intermolecular force. Okay, whereas if you see that this dude. If you see this dude on top of the surface, the liquid surface, right? It is actually experiencing unbalanced intermolecular force. Why? Because below I have my own people, right? Water. I have my own buddies that I hang out. I have this hydrogen bonding that's going on. But above me, it could be air, right? But my bond, the bond between me and my buddy, another water, and versus the bond between me and the air, that's two different bonds, right? So I'm experiencing unbalanced intermolecular force, right? So that's why on the surface, I have some sort of tension, okay? So it's actually the unbalanced intermolecular force that causes the surface tension, right? And then when is the surface tension high? When the water molecule really likes its own buddy, right? When I really just want to hang out with the other water buddies, I don't want to get anywhere close to the air, right? I don't want to have a bond with the air. I just want to be together with my water molecules. Then when the intermolecular force is really strong, then the surface tension will also be really strong, right? Oh, in other words, if there's weak attractive force between the liquid and the air, then it will also favor the surface tension. The surface tension will also be high, right? Same meaning, okay? Different expressions. Okay, so before we move, let's now talk about the unit of the surface tension, okay? So the unit of a surface tension is basically a force divided by length, right? So the SI unit for force is Newton, and then the length is meter, right? Or it can be energy per area, which is meter cubed. Oh, meter squared, sorry. Okay, so they're the same thing, okay? That's the unit for surface tension, okay? And then to relate it to biology, in our lawn, there are a lot of alveoli, right? So the alveoli surface area is very large. That gives it a large amount of surface tension as well. So that we produce surfactants to lower the surface tension, right? So that would prevent alveoli from clasping in lawns, okay? All right, so now let's move on to cohesion and adhesion, okay? So what is a cohesive force? So cohesive force is basically the intermolecular force that we've been talking about, that links the molecules together, that generate the surface tension, okay? So if a thing has a strong, we say cohesion, we say, oh, it has a very strong intermolecular force, right? For example, mercury. Oh, okay, let's actually discuss adhesion first before we move on to the example. So adhesion, on the other hand, is what? Is the force, the attractive force or bonding force between the liquid molecule and the container, right? So if the liquid molecule doesn't want to hang out with its own people, it just want to get closer to the container, then there's a stronger bond between the liquid molecule and the container, right? So let's see the two different cases. So if a thing has a stronger cohesive force than the adhesive force in the example of, let's say, liquid mercury, right? Then the thing would really like form this convex meniscus. This is mercury, right? Because it really want to just hang out with its own buddies, right? It doesn't want to have any contact with the container, so that's why it's kind of like a hugging into itself, right? Having this convex meniscus. Whereas let's say water, right? Water is something has a higher adhesive force than cohesive force. Then if you put a water in a container, you will see something like that, right? Excuse my drawing. Okay, so this meniscus is convex. I mean concave, sorry. The other one, mercury, is convex. This is concave in case of water, right? Which means a water molecule kind of enjoy, hanging out with the container than hanging out with its own buddies, right? Okay, perfect. Now the last idea of this video is a capillary action, right? So what causes capillary action? So capillary action is the interplay of adhesion force and surface tension that allows liquid to raise up. It can raise up the tube, right? Or if you remember the thin layer chromatography OChem 1 lab 1 experiment that you did. You put a piece of paper in a beaker, and there's liquid in the beaker, right? And then the liquid would raise up, right? It shows on your paper. So that's the capillary action, right? So and the option is always in opposition to gravity. Okay. Another example is the plants absorb water in the soil, right? So the water liquid would kind of raise up the stem of the plants. So that's how the plants can absorb the water from the stem. Okay. All right. So that's all about this video. I think it wraps up all I want to talk about hydrostatics. And then the next video, we're going to move on to hydrodynamics. We're going to study when fluid is in motion. I hope it helps. Thank you.